Good afternoon. Welcome to my talk about the UEFI subsystem in U-Boot. My name is Heinrich Schuchert. My name is Heinrich Schuchert, and I'm working in my paid life as a software consultant in the ERP and in the supply chain area. But I've been contributing to U-Boot since 2017, and I've been, since the beginning of last year, the maintainer of the UEFI subsystem in U-Boot. And now you may wonder why I got there, and this is what I will start my talk with, and then I want to dive with you into the internals of UEFI so that you understand how UEFI really helped me to solve my problems in booting from the network. So let's start it. So why do I want to boot from network? So I had a few little boards of the Raspberry size, not Raspberry itself, and the fastest connector on these boards was really the Ethernet port. They didn't have SATA, they didn't have PCIe, and of course you could plug in a USB 2 converter to a SATA drive, but a SATA drive still cost me more than the board itself. And so I thought network booting would be the natural choice to carry on. And network booting exists in U-Boot. So you can set up a boot P or DHCP server that will provide the address of a script. Then the script can be downloaded via TFTP, and then you can boot from an NFS server. But unfortunately, as U-Boot only supports UDP, this server has to be set up that it's running by UDP. There's no authentication at all, and I thought, oh gosh, that's not what I want. And then I knew, of course, what we were using in our company, and typically in a server environment, you are running iSCSI, or you're running using fiber channel or whatever. So iSCSI is not like Samba serving singular files, but it's really providing a block device. So it's like just a virtual hard disk that you have where you can put your own partition table on and then create your partitions, and then you will have your boot partition and your home partition and your root partition. And it offers really authentication. So the server and the client can mutually authenticate each other. It's the chat protocol that's being used, so there's some common secrets those two parties have. They use some challenge, so that it's always the same being transferred. So yes, you cannot have replay attacks. And if you need more security, you could separate, of course, your storage array network from the rest of the network via VLAN or use IPsec for encryption. So this is what I wanted to do with my board, which was running U-Boot. And U-Boot is one of the most common firmwares for those little boards for booting. So I looked at the specification, started implementing a bit in iSCSI, and saw it's tedious and hasn't anybody done it before? Why should I do it myself? And that's when I came upon a software called Pixie, where the main developer is Michael Brown. And it's just like a Swiss Army knife. It implements lots of different protocols. The origin of it was just a replacement ROM for your network card for doing Pixie booting. But now it can support booting from HTTPS server, from iSCSI, that's what I'm interested in, can boot via fiber channel over Ethernet or ATA over Ethernet. It has its own scripting language, and it can be built as a UEFI payload. And that's when I thought, okay, on my workstation at home, I'm having UEFI booting my x86 computer. So does this also exist for U-Boot? Yeah, and in 2016, Alexander Graf, at that time working for SUSE, now it's at Amazon, he was really starting to implement the UEFI standard inside U-Boot. So the driving side for his company, SUSE at that time, was that they wanted to boot all devices the same way. They said, if we boot a server by grub and then grub loads a Linux kernel, we want to do the same on a Raspberry too. And that was why SUSE was interested into getting UEFI into U-boot, which was running on those small boards. And I said, oh, it's complete. So I have iPXE, I can compile it as an UEFI binary, run it with U-boot, and great. That's what happened. I just got a return code, a bit cryptic, but if you convert it to a hexadecimal and look it up, okay, you see it's error code 9 out of resources, because there was only one event possible. That was really the reason. I said, okay, maybe now everything is there, let's try compiling a hello world. Just writing hello world on the console and then do a return statement. And it crashed again. Because Alexander assumed that every executable would exit via the exit API call. And that's when I really thought, okay, that seems to be really something that has been started but needs some support. And that's when I got into this. So I started sending in the first patches mid of 2017, when there was really, it could barely boot grub, and with grub you could really boot into Linux. That was working, but nothing else. And in 2018, with the May edition of U-boot, I could finally really run iPXE and boot from my iSCSI server. And of course, the voyage was not finished there, so it was still not really conformant with all the details of the UEFI spec. And finally, last year, we got it to a point that we could run the UEFI shell. That is a shell like the DOS shell, really primitive, but you can run different binaries, you can set variables, you can have a small editor even in there. And this is the basis that you need to run the self-certification test that Live and Art had been talking about. And so I have written about 60% of the UEFI code, but there were in total 40 contributors contributing to this to get it running. And now you may ask yourself, where's really UEFI sitting? Because when some people talk about UEFI in the x86 world, they're just talking about as if it were the whole BIOS, if the whole firmware is UEFI. No, UEFI is simply a standard. It's defining an API. The question is, where is it used? So what I've put here on the board is just the boot process with ARM trusted firmware as it's running on 64-bit ARM CPUs. So where does it start? Really, the CPU has a little ROM with which it loads the first part of the ARM trusted firmware, which then boots the BL2 trusted boot firmware, which then boots the next part, loading BL31, which is the exception level 3 runtime. In this runtime, you find things like the power state coordination interface, which is responsible for resetting a board. So they provide already an API, which then can be called by U-boot for resetting a board. It can, but it not always does, also boot in the secure world an extra operating system where you can run, for instance, opt. This will come in handy if you really want to have secure boot, because we could use it for storing variables. That is something that Linao is currently thinking about. And yes, of course, the BL31 also loads BL33, which in our case is U-boot. But there are, of course, other implementations like Tiano Call, EDK2, like we heard in the last call. And now U-boot or EDK2, they are offering this API, which is defined in the UEFI spec on 2,500 pages. And now this spec defines different API calls we will look into, and these can be used by grub or by iPXE to communicate with U-boot or EDK2, and they can also be used in the Linux stub for the same sort of communication. So when we now start a UEFI binary, what is the first thing that it sees? It simply gets a pointer. It gets a pointer to the system table, and the system table contains different services that are available. And by these services, it can also discover some protocols which offer additional APIs. And we have two major parts in there in the system table. The one thing is boot services. This is what is available until really the operating system is running. And when it's running, only the runtime services are left over. For instance, those services that are necessary for rebooting or setting boot variables. And there are also configuration tables passed. We heard Art that he said, okay, currently we are passing the device tree. Can't we get rid of passing the device tree in here as a configuration table? The servers use instead ACPI, and also we have an SM BIOS table passed. And if you look at the protocols, they are really providing things like network access. They are providing access to block devices. So if you now look into what are the atoms really of UEFI, the two object types, they are one thing is handles. This is just a pointer on which protocols are installed, and there are events that are triggered by a timer and then called back into the binary. Or they can be triggered by a call of one of the services. If you think about what is the lifetime of such an object, of such a handle, it's created when the first protocol is installed, and it's deleted when the last protocol is removed. When we look into drivers, what will be coming interesting in a second is a driver is simply a handle which has a specific protocol installed on it. So it's a piece of software that when it's installed, the handle is created, the API driver binding protocol is installed in it, and here you see what really protocol means. A protocol is just a structure, a pointer to a structure. And it's a GUID which identifies this protocol. And in the protocol interface, for instance, of the API driver binding protocol, you find there are three functions in it, supported start, stop, and there are three data fields, which version, the handle of the image that was loaded to get the driver running, and the driver binding handle. And on the other side, of course, there are the devices, also in the specification sometimes called controller. And that is a handle which has an API device path protocol, and which you could use just to get an overview of what devices really exist. I've just printed out what I had on my laptop, where you, for instance, see, okay, there's a PCI root. On the PCI root, there's some NVMe drive, and on the NVMe drives, there is a partition existing. And the same thing also for on the SATA side. These were examples just of such devices that exist there. And now how are drivers and devices attached to each other? In the boot services, there's a call called connect controller. And this one calls the supported function of the protocol, finds out whether there's a match. Then the start method is called of the driver binding protocol. And then the driver is really started, and it installs its own protocols on the controller. So for instance, if you have a hard drive and the hard drive asks, okay, who can serve me, then maybe the controller will install a fat file system on it. And it also may create child controllers or extra handles it may create. And if you now look into how this is put into the picture with iPixie, on the right side I simply have some parts of U-boot. So in U-boot there is a network driver. For the network driver inside U-boot there's a simple network protocol exposed. And there's also some driver existing API block device which exposes the driver binding protocol for block devices. And now when iPixie is loaded and running, then iPixie installs a TCP/IP driver. This is necessary because U-boot only knows UDP. it installs an iSCSI driver and uses this iSCSI driver to connect to the server and installs on the drive that is connected to a block I/O protocol, and then calls connect controller. And this connect controller then reaches out to the block device driver in U-boot, which then uses the FAT driver that exists and the logic for identifying partitions to expose a simple file protocol. And this simple file protocol then can be used by Pixie to actually load grub or directly load Linux. And essentially, grub then will do just the same thing. Grub will, when it tries to load something, it will call the simple file protocol, which internally calls the FAT driver. The FAT driver calls the UEFI block driver, which knows, OK, I'm connected to that handle with the block I/O protocol, which links back to the iSCSI driver. The iSCSI driver, by the TCP/IP driver, calls the simple network protocol driver, and then loads the different blocks of Linux and of the initial RAM image. This is how these all go together. I have here a short movie. Oops, maybe it will get it. So that's where it's actually starting to boot. So here first of all, U-boot tries to find its own devices, like USB devices. It finds its SD card, and then a script is running which simply loads iSCSI, known as IPXE. Pixie loads grub, and then grub just continues as we know it to load the Linux kernel. So yeah, for me the takeaway really was, yeah, by providing a common API, we really can run standard software on U-boot, which before that we could only run maybe on a PC that had an UEFI BIOS or which was running Piano Core or whatever. And now suddenly we can run things like grub, like iPixie. So when we think about, okay, what was problematic in doing all this, the one thing really that was nasty about U-boot is that it's running single-threaded. It has no network interrupts, and so especially for implementing events in lots of different places, one really had to call back into some routines that would handle event queues and know, okay, he was waiting for an event and call those functions. So that was one part of the nastiness in it. Another thing is U-boot is more than 10 years old, and of course it comes with its own history. And the model how drivers are implemented in U-boot is currently changing. It's trying to get more modular. There's a new model based on device trees installed inside U-boot, but it's not used everywhere. And this really stops us from getting a very tight integration between the UEFI code inside U-boot with the drivers. It really sits more on top of it than being really well integrated. And that's something we will have to work on once we get the driver model really firmly established. Yeah, when we look into what are the development targets for UEFI inside U-boot, it's not the idea to implement all those 2,500 pages and then come up with a binary which is several megabytes long. The target of U-boot has always been it should boot on a very small board. And this is why we will only implement a subset of UEFI. There has been an effort led by ARM to define a restricted subset, which is called the embedded base boot requirement specification, which is available on GitHub, which requires that you have, okay, all the boot service in place, you have the runtime service in place, and there's one chapter which defines some other required elements that you should have. And we really want to stay small, so I often get complaints the UEFI part is already growing too much. Currently it's at something like 70 kilobytes in the firmware, and nobody will be happy if it gets much bigger. So what have we achieved last year? Now we have all boot servers in place. We have had, as I said, we were able to run the UEFI shell, which allowed us to do self-conformity tests, and with this conformity testing using the SCT, we were able to fix a lot of differences to the specification, especially conformance issue where we're not checking incorrect variables being passed. And yeah, we can run the UEFI shell on ARM on x86. We can run the SCT. And now let's finish off with what is work in progress. We have just merged a work by Christian Caltea so that we can have a verified boot, which is based on fit images. There's Linaro with Takahiro Akashi working on UEFI secure boot. What we already have merged is support for hardware the number generators, and so I'm confident that we are improving it bit by bit. Thanks a lot for your attention, and it's up to your questions.
Questions?
Yes, please.
So, an IPXE binary is usually not that small. So, do you store that somewhere on the system itself, or do you load that over TFTP?
No, the question was where is IPXE located? I personally always load it from the UEFI partition. So I have an UEFI partition where I have this on, and I have the device tree on. Essentially, I have the firmware, the device tree, and IPXE on my SD card.
So you have to have an SD card?
Yes. And everything else, grub, the kernel, and the RAM disk is then loaded via iSCSI. Yes, please?
If you say you want to stay small, how do you decide which part of the UEFI specifications you want to properly implement or not?
Yeah, it's essentially what is in the EBBR, what we want to have. So the question was, which parts will we implement, and that's why I mentioned the EBBR. And we have implemented some extra things that were necessary to run the shell and to run the conformity tests, because they require some protocols that are not in the EBBR. Yes, please?
So if I understand this correctly, once you have the system table and some of those protocols that you need, you can now load UEFI drivers once you booted this UEFI subsystem and use those drivers to drive some devices if you don't have a UBoot driver.
In principle, the question was, can we really run extra drivers? We have everything in place, but I have not seen any implementation really using this. So currently, in U-Boot, there are drivers for all sorts of storage devices and for network and for USB. And at least the network and the storage devices we are exposing via UEFI protocols without any extra driver having to be installed. But if you say there is some sort of special device which you want to expose, then you could load a driver that you have written yourself. Yes, this is in place. Yes, please?
It's parts of if you want to support more than the EBBR, for example, I don't know if it's enough with Windows, it's possible to also configure out parts of the UEFI spec that you don't need to save space. So that you have a configuration option for every boot protocol, for every...
Yeah, the question was how configurable is the UEFI subsystem? There are parts, or if you look into the configuration of U-Boot, it's like configuring a Linux kernel. We are using just the same kconfig system, and some parts are optional that you can leave out, or you can completely eliminate the UEFI subsystem if the board is really too small. So there are some boards that only have place for 300 kilobytes of firmware, and there you cannot have the UEFI subsystem. But if you have 600 or 700 kilobytes, it will well fit in. Yeah, then thanks a lot for your attention.